Christian, the stage is yours.
Yeah. Hi, welcome back to another wonderful etnaviv talk. This time I would like to talk about the wonderful world of performance counters. If you missed my talk before, my name is Christian. I'm a long-term etnaviv developer. I live in Austria near the Lake of Constance, and there are no kangaroos. So I'm a first-time speaker, and I hope to get it right. So let's start. I want to talk about GPU performance counting in general, then the specific thing about etnaviv GPUs in that regard, how the binary blob solves it, how we do it in etnaviv, and what feature topics we have regarding performance counters. So I think everybody of us knows the situation where a random person hits you up and tells you, hey, my application is running slow. What shall I do? And I'm in that situation and I tell the guy, I'm not really sure. It can have multiple causes why this application is performing bad, and it can have multiple causes why it's performing better than the binary blob. For instance, we could miss some extension, etc. support in etnaviv, or we are simply doing too much stuff. We do an extra blitz where no blitz are needed, or stuff like this to waste too much bandwidth on the system. So for this, we can use performance counters. They can help to analyze the performance and execution characteristics of applications. Wonderful. I think that every major GPU manufacturer has some tools to visualize such performance counter traces. In my case, or in etnaviv case, there is a vAnalyzer application where we can look at the different performance counter values and try to figure out what goes wrong. So there's now one special thing about the GPUs from Vivante. This is a really hard one. You cannot access the performance counter registers values from the command stream. There's only one little exception to this, the occlusion queries, where you can really define in the command stream the address of the occlusion buffer where the hardware should write the actual value. In a normal case, there should be a way to access the performance counters from the command stream, because it helps you with a lot of stuff, which I'll go into deep a little bit later. But during the preparation of this talk, I found out that there might be support for this feature in the coming GPU generations, because there is a feature flag called GCV feature probe. And if you look closely into the public Git repo for the Linux IMX tree from Coderor, you find some interesting informations. Sadly, I have no GPU which supports this feature, so it's something for the future. So, as we know now the limitation of the how we need to, or how we can access the performance counters, we need to work on a solution to provide the performance counter configuration values to the user space in the end code. So with that knowledge, we know that only the kernel can access these registers. There are some simple performance counter registers where you just read the register and be safe. Then there are more complex registers where we have a multiplexer, where you need to configure the multiplexer to select the wanted performance counter source. And then you have a separate register where you can read out the selected performance counter. And there's another special thing where you have multiple pixel pipes, you need to iterate over the pixel pipes and do the max config read-write thing to get the per pixel pipe specific value. And you need to take care of stuff like clock gating, and you need to enable debug register access for some kind of performance counters. So it sounds quite easy to implement this, or let's move on how the Vivante provided Gallcore kernel driver does this. As I told you before, you need to enable and disable the profiling mode to ensure that clock gating is disabled and that the debug register access is enabled. And for this, the Gallcore kernel driver provides some commands, the get profile setting and set profile setting, to switch on and off the profiling environment. Then there's another command that allows you to define what should happen if you have read the performance counter value. Should it be cleared or not, for instance? So now we know how Gallcore configures setups the performance counter context. Now we need to read out the performance counter registers. And for this, the Gallcore interface uses 3 other commands. One is specific for the 2D core. That's the profile registers 2D. And then for the 3D core, we have a profile registers part 1 and 2. So with that in mind, the hardest part for etnaviv is now to figure out the MUX configuration. What MUX config relates to what kind of performance counter value. The good thing is that Gallcore also is a nice register documentation. For instance, if you look here at this excerpt from the Gallcore driver, let's say we want to read out from the pixel shader how many branch instructions there were during the overall runtime. We can look it up in the kernel driver they provided. We can see here that we select the correct, hopefully correct MUX configuration. We select a certain signal, I call it, and we configure the MUX. And later on, we can read out the selected performance counter value. So quite hard to read such obfuscated code, but it works in the end. You know what to look for. And the thing with Gallcore is that over time, over new releases in Gallcore, they add new unknown performance counters. So it's also always nice to have a look at the kernel driver source code to see what's going on there. So now we have a rough picture how the performance counter readout with the binary blob could work. It looks like that there's some cyclic event readout triggered, and that all performance counter values are read out and stored to some magic file where the VAU analyzer application can look at it and present results, and the developer is happy. So now we need to come up with something for etnaviv. There are 2 ways to approach this. We can go simply the way Gallcore does it, which means we have one I/O control and read out all counters in one go. Sounds simple, but is it the right solution? From a development standpoint, it is really easy to implement. You have 2, 3 I/O controls you need to support, and you simply read out everything. Quite easy. But there are, from my point of view, some problems with this approach. For instance, we need different I/O controls for different pipes. Pipe is a concept used in etnaviv. A pipe can be a 2D core, a 3D core, or VG core. And the approach the Galco interface has chosen is to have different I/O controls, commands per pipe. And I'm not really happy with this design decision, but I could live with that. The next one is a little bit harder. You need to be ABI compatible. If you add newer counters. The nice thing about Galco and the binary driver is that they are tightly connected to each other. If you run Galco kernel drive in version X, you need to use the Galco binary blob in version X so that they work together nicely. The Vivante team does not care about ABI compatibility. So the next problem with this whole approach in sampling, cyclic sampling, one-shot sampling, or I'm not sure how I should call it, there is really no relation to a specific draw call. And I think that is a quite important thing. If you want to analyze one frame and see what the GPU is doing, it is much more helpful than having a rough overall state. Because keep in mind, the CPU and the GPU are not synchronized to each other. So the time when you sample the performance counter values in one go might not really reflect what you're looking for. It might be before your draw call, after your draw call, in the middle of the draw call. So you only get the rough overview picture of everything and not the really zoomed in way into a one draw call. So that was no way for me to add support for performance counter. So I needed to come up with a different solution for the same problem. How about emulating the missing counter access from the command stream? It takes much more time to get it right, as we want to be stable API and ABI-wise, but it can be done. One plus point would be we have one interface for every kind of pipe. We can use the same mechanism for 2D, 3D, and VG cores. We can easily extend new known counters without breaking any ABI, as we have no fixed offsets where one counter needs to lie in memory. We have no limitations in size of the structures used, etc., etc. So another plus point. And the biggest for me is that if we can emulate a register access from the command stream, we can easily get the relation between a specific draw call, which is super helpful in my eyes. And also, if we go that route in emulating the missing counter access via the command stream, we can easily support the so-called one-shot readouts like done by the Galco kernel driver. So how can we do this emulation in a command stream? etnaviv kernel driver uses an in-kernel command buffer, a circular command buffer, where it queues in, or it jumps to the user-provided submit I/O controls command buffers that you get from the user space. And in between there, we now do stuff. We do cache maintenance, we do pipe switching stuff, and we can also do something to emulate this readout of the performance counters. So in order to the hardest part is to get everything synchronous. Also that the GPU and CPU are doing the same. They are halting at they have the same expectations where the GPU is. For this, we modify the in-kernel command buffer if we queue in a user space buffer, and we trigger an event, which is the same as an IRQ on the CPU side. Then we stop the FE. The FE is the fetch engine. It's more or less a fancy DMA controller responsible to process the command stream. At that point, we know now that the GPU isn't doing any rendering stuff, etc. So we can now process the IRQ on the CPU side and do some work in the driver, whatever this work might be. If we are done with this work, we can easily restart the fetch engine and everything continues like before. This sounds quite terrible in the standpoint of performance, but I think that when you're doing performance counter measurements, you're really interested in correct numbers and not in the overall performance of your application. So yeah, and this whole thing in the etnaviv kernel driver is called a sync point. So we have now the possibility to really stop the GPU at the defined state or the defined position in the command stream, do some actions, and move on in the processing of the command stream. With this little trick, we can easily do the emulation of the performance counter readout in the command stream. In order now to make use of this mechanism, we need some kernel interfaces to provide access to the performance counters for the user space. We need to get the list of possible performance counters. We have chosen the way to store the possible or the available performance counters on the kernel side, as there might be some hacks, some changes over the lifetime to read out a specific register, a specific performance counter value. Then you can do the correct logic in the kernel and don't need to do a lot of dancing in Mesa. We need a kernel interface to configure the readout, hopefully via the submit IO control. And we need some way to expose performance counter data to user space. So let's start with the simple one. The simple one is we need an interface to define all possible performance monitor domains and signals. We have chosen to put this into the kernel, and we have one big structure, a structure where we, for instance, in this case, we have a performance monitor domain called SH, which has 9 signals, and I have put one of them here on the slides, the shader cycles. And as you can see here quite nicely, we have in the domain struct part, we have a profile read where we define which register is used to read out the selected max value. And we have a profile config field, which defines which register is used to configure the multiplexer. And in the signal part, we have a struct member describing which value needs to be written to the multiplexer configuration. And also we define the name and how the readout should happen. If you remember, we have 3 different cases for performance counter readouts: the simple register read, then the max read, and the pixel pipe readout. So now we need to define the IO control interface for this. And we have one part to query all performance monitor domains. For a specific pipe, remember a pipe can be 2D, 3D, or VG. And we get per the domain the name and how many signals the domain have. And then with that information, we can query the different provided signals for a pipe and domain combination, and we get the name of the signal out of this interface. The next part would be the user space now has access to all counters that are possible to use. Now we need a way to provide a mechanism to read out these performance counter values for a submit. A submit is basic, so we need to have two different positions where we do the processing of the performance monitor readouts, because we want to read out the performance counter before we do the actual draw, and we want to read out the performance counters after the actual draw. That's the two defines the process pre and process post. Yeah, and then we need to define a same way that the user space has a possibility to store a selected performance counter value at an offset in a provided buffer object. And and we need to provide a way to define when the sampling of these performance counter values should happen. With that, we can extend our submit IO control. We can now specify how many of these performance monitor requests we want to execute for this specific submit. This makes it possible to sample a well-defined number of performance counters. So we don't need to read out all possible performance counter values, but we can specify we will only want 2 or 3 of them. With that, we have now a pretty sane, in my opinion, sane interface for the user space to work with this kind of performance counters. Now the next thing is, how should we integrate this into our Gallium driver? We went that way that each pipe query has its own buffer object. Remember that in the submit IO control, we just define the number of performance monitor requests, and in every request, we define where to store, at which offset of the buffer object would you like to store this specific value. That's why we have, that's why every pipe query has its own buffer object. Then we implemented the begin query, end query, get query results to work with the performance counter monitor, which means when the begin query function is called, we simply add a performance monitor request to our submit IO control, to our submit structure. And we add a performance monitor request to the submit, where we define that we want to sample it before the draw starts. And the same happens for the end query, but we add a performance monitor request to the submit with the sampling time post, which means after the frame has been drawn or the draw job was executed. With this, we can now really sample the performance counters before and after we do the draw. Now, the interesting part is, how do we get the results back? Basically, we do a CPU prep to get access to the buffer object, and there's a little trick used. Every time we add performance monitor request to the submit IO control, or the submit call, we define an expected sequence number. And when the kernel part processes the performance monitor request, it stores the expected sequence number at offset 0 in the buffer object. With that, we can easily check if our query is done or has a result, let's call it that way, by checking the sequence number. If the sequence number matches the expected one, we can simply process the written values and do our stuff. And after that, we call CPU fini to give the buffer back into the GPU domain. Now we have one simple problem. We need to take care when flushing happens, because we need to stop the active queries, flush the buffer, and begin again. With that in mind, we store multiple value pairs in a buffer object for one query. Now we have everything hooked up into Gallum API, which gives us the possibility to use the Gallum HUD to stare at the performance counter values to get nice graphs, how they evolve over time. And also it is possible now to use the AMD Performance Monitor OpenGL extension to interact with the performance counter values provided by the GPU in the same well-defined interface that can be used by tools, which is really, really nice. So we have now the basic stuff laid out, everything works, but as you can imagine, we are not done yet. There are a lot of stuff that is interesting too, besides the basic performance counter values. One of them is the load values per, call it engine in the hardware. And there is work in progress thing I got here running. You can see here the Gallum HUD showing the load values of different engines, different engines for different use cases, or different scenes rendered here. This is mostly work in progress at the moment, as I had to talk to a lot of guys how they are doing it for their hardware, because I was not really sure how to model the user space kernel space interface, as the etnaviv GPU has one idle register where each bit represents one of the engines here. So I wanted a sane interface, and this takes time, but I hope to land support for this quite soon. Another interesting thing that would be nice to have are bandwidth values. There are performance counter registers or MUX configurations to read out, for instance, how much bandwidth does our fetch engine consume, how many blit reads are we doing, and stuff like this. The biggest problem here is, again, getting the kernel user interface right. I could expose these values by the current performance infrastructure, but I'm not really sure if this is the right thing to do. Also, I need to verify what happens if these bandwidth counter values overflow, if I need to reset them or not. And what also blocks me at the moment is that I'm not perfect in handling big patch queues. So I try to land one thing after another and don't want to do much in parallel. But I think with these bandwidth numbers, we also get a much better insight what's really happening, or what is really happening inside the GPU, and where we can take steps to improve the performance. Another topic that got a lot of attention recently is this thing called perfetto. This is system-wide profiling thing where you get a really, really nice overview what's happening in your system. There is some proof of concept, I might call it. I'm not really sure, but there's, I think, pan-first support at the moment for the performance counters, and I tried to hack in order to hack etnaviv support, but at the time I looked into it, the perfetto GPU integration was really fixed on pan-first, and in my eyes there's a little bit work needed to support different GPU providers. But overall, I have work in progress patches to support this feature too. Now, in contrast to the per frame performance counter values readout, perfetto works on like the gallum profiler. So you do a cyclic readout of all the interested performance counters without a really relation to a specific draw, to a specific frame. And yeah, I hope that we can land support for perfetto too. There are work in progress patches. Basically what we are doing at the moment, we are enabling and disabling the power gating and the clock gating and the debug register access on the fly when we need to process a performance monitor request. In order to support perfetto, we need something like the gallum kernel interface has. We need a way to enable a global profiling mode where we turn on the access to the debug registers and disable the power gating overall for a longer period of time until it gets disabled. Yeah, and there are work in progress patches to support these scenarios. Another interesting thing to support perfetto is how should we expose the red performance counter values? Because currently we are using buffer objects to let the kernel store the values in there. So we would need here another sane interface that supports the readout of a handful of performance counter registers values, and we need you use normal system memory instead of a buffer object. But in the end, I see no big showstopper for perfetto support. So overall, we have, I think, now a really great picture how the performance counter stuff on etnaviv works. And I was really happy that I got contracted to do this work. And I think it turned out quite nicely. It was, at the beginning, I thought it would be a lot easier to get stuff done. But with all the special cases you need to take care, it took a little bit of time. But I'm really happy that everything landed is in the upstream repos. You find it in the kernel repo, in the Mesa repo. So you really can consume performance counters on etnaviv. Yeah, sadly, I was a little bit too fast. So thank you, everybody, for listening to me, and I am open for some questions.
Thank you very much for your talk, and let's see if we have any questions on IRC. So I just see, I know that yes, the perfetto GPU collection does need to be a bit more generic. Patches extremely welcome. And another note that even NVIDIA isn't that bad, so...
Yeah.
So I guess that's it. Thank you very much for your talk. And